Now, what we will do first is we have to first collect together all the apparatus we are going to use. Then we know that this one is a spring balance. It is labeled. It has a scale which is labeled. Whenever you insert a mass, like when I insert this mass, then I expect it to be going down. This mass overwards. Then whenever I put on a mass like this, this one moves. You see that? Now, what you do, for you just to read on the scale, which value is it showing on the scale? Then I can also reduce on the masses. When I reduce on the masses, you'll see it going upwards. You see that? When I add on the masses, this one moves downwards. When I remove the masses, it goes back to 0. Now that is how the spring balance works. Now, this one is a text tube and it's called a measuring cylinder. It is labeled. This one is the cubic centimeters, not cubic meters. Then centimeters cube. Now, whenever it moves up, here it has values. If you see here, it has 100. Here it goes to 200. But there are these small ones, 10 of them. Each of it is 10, 10. If you reach here 100, 110, 120, 150, 40, 30, 140, 150 here, 160, 170, 180, 190, this is 200. You get that? Now, what we are going to do is that we want to, because we have to follow the procedure, this is how the physics practical has to look. We first get the aim we are doing. Now, our main aim is to get the density. We are calculating the density of this solid. Now, if we are going to get the density, remember we can get density can be obtained from when we get the relative density of that solid, then we multiply that 1,000. This is the density of what? Density of water. Now, this is how we shall obtain the density. Now, what we shall do, our experiment, we shall mainly focus on getting the what? The relative density. Now, it means that our main aim is getting density, not getting the relative density. Because relative density is just part, but it's not the density. Now, our aim is to get the density of this solid of ours. Then we shall hypothesize, we shall say that our density value has to range from this value to the other value. You get that? Now we shall hypothesize at the end. Then from there, independent value. Which one we shall make independent, which one we shall make dependent and fixed. We are going to conduct 2 experiments. One of them of balancing. We shall see how these ones work. This one of using a split balance, no need for independent and dependent. You just sit deep into water, you wait in the air and other stuff will go on. Then apparatus, you enable the apparatus we are using. First of all, we have this mass. These are the masses we want to get to their density. You put them aside. You say, I'm having masses. Then from there, we are having our spring balance. You say, I'm having a spring balance. Then from there, you are having a measuring cylinder. Then you go ahead and write the measuring cylinder. Then from there, you are using a little stand. You write it there. Then from there, you draw a diagram. Remember, I'm also having a thread on a spring balance. You also have to indicate that I'm having also a thread. Then the next part is drawing a diagram. Then after you draw a diagram, you will say that I will have my measuring cylinder like that. Then from there, I will have a spring balance, which will have a scale. Then I will have the masses of mine, and they will be dipped into water. Now this one will be measuring the weight, and here I'm having my little stand. You draw something that resembles the real one, however much it might be funny. Now you label and you say this one is a little stand, then this one is the measuring cylinder, this one is the spring balance, these are the masses, and this one is water. Now water is transparent, that's why we're going to use the colored one, so that we can be seeing how it will be moving along here. So local lava is either moving up, whenever we dip the solid into the water, will it go up or it will stay the same? Because we say that when we are getting relative density, we have the upthrust part. And we say upthrust is equal to the weight of the what? Weight of the what? Upthrust is equal to what? Zam, you know, I said you resemble something. Now, it will be equal to the weight of the what? Of the fluid displaced. It means whenever I dip here, there must be some fluid that will be displaced. It means when I weigh that fluid displaced, and also when I measure the weight here has to be the same. The weight of that fluid another displaced. When I get it, like you getting that of the fluid displaced, we'll use a displacement can, the one that has a spot here, that water can go out. Then we measure that weight of that water that has moved out. What you saw in the notes, in the notes there is that one which has some. Now what we are going to do is that we are going to put our colored water into here. I don't know whether this one will continue to be sticking. Can we see the scale? Will this one get off?
We shall add in some pure water.
That one I think will be enough. Now it is in something like, let's make 600. 600. It is in 600. Now we are exactly at 600. Now what we are going to do, we know that for us to get the relative density, we know better in the expression that the relative density, this one is equal to when I get weight in the air over the upthrust in what? Upthrust in water. Now it means my relative density has to be weight in the air over the weight in the air minus weight in what? In water. That is how I can get my relative density. Now, me to get the weight in the air, it is easy. I just do like this. I get my solid which I want to get its relative density. This is my spring balance, which is exactly at 0. Then from there, I can load it in. It was at 0 initially. Then when I put on this mass, it has some value. Someone can come and read it. Someone come and read the value. Now, if you observe well, it has the part which is grams. It has a part which is in what? Newtons. You choose any you want. Now, which one are you choosing? Grams or newtons? And then you read well. The value is what? 2.0 newtons. It means the weight in the air of ours is 2.1. Weight in the air is 2.0 newtons. Then from there, I want to see its weight in water. It means you have to be keen. And never forget that this cylinder of ours, we have maintained it at 600. Now we want to see whether will that water rise, because we see when we put something there, the water has to be displaced, and we call that one upthrust. If we get the weight of that displaced water, when we dip this one into this water, will it stay at that same size of 600 or it will rise? You get that? Now we are going to put our solid there. We shall put it well. The reason why I'm using a thread so that I can easily dip it there. Then I'm going to dip it there slowly. I want you to observe the water. Observe the water. Will it rise or it will remain at the same value? We dip it until it is wholly immersed in water. As you see, it is wholly immersed. The whole of it is immersed. Now you read off. Is the value increasing or it is remaining the same?
It is increasing.
It is increasing up to what value?
6.
Yeah?
630.
680. It means it has increased by 80 cc's.
It's 630.
30. It has increased by 36 is. You see that? Now, you read off also the value in weight. So that someone can come this side because it's like this. You see the weight.
It is 1.75 newtons.
1.7 what?
5 newtons.
1.7. The other one was?
2.0.
It means there is that loss in the weight. If you observe well, now that loss in the weight is the one we are dealing with. Now, the weight in what? In water is 1.7 what? Newtons. Then you can feed it into this expression. You say that, now you say that your relative density would be a 2.0 over the 2.0 minus 1.71. 5. Then someone with a calculator replaces this and gets the final answer.
You get 8.
8. Now, it means if I want to get the density, I'll get the relative density times the density of water, which is 1,000, which will be 8 times what? 1,000, and at the end I'll get what?
8,000.
80,000 kilograms what? Per meter cubed. Now, can we get that same value when we use another procedure? You get that? Due to the concept of physics, they are right. If you follow all the rules well, everything has to come out when it is the same. That is physics. It's not like you have used the other formula and you have to use a different one. Now the one you are using is wrong, but no way. You get that? Now we are going to use another way of not using the spring what? Spring balance. So then I will get my spring balance and the little stand. I'll say, then we put this one to what? I hold it, then I'm going to balance and see will my things work. Then now I'm going now to use the principle of moments. When I balance like this and that, what can happen? Now, since I'm in the due process of balancing, I don't need how to see how these scales are moving. We know that when we dip something, water will rise. Because we have seen the other one was rose from 600 to 630. Then there was an increment of 36. Now what we want is to balance, and we see will our things work, then we add in more water. We don't need to know whether it will rise or not. You bring the other water in. Now we add in more water. Just like that. Now we want to balance using principle of moments. Then we shall put in then we put on this one and we see. We need to balance when this one is up. You see now now this is how we are going to mitigate the errors we are going. These are the challenges. The challenges we are facing, we are going to call the errors. When I use one wooden block and I put on a knife edge like this, it cannot balance this one. You get that? Then it means I have to add on another like this. Then I try to balance. With it a bit at the top, you see it is just touching, it can never balance. It means I have to improvise. I add on another one like this. Now when I try to balance, what will happen? Now this one can balance. You see that? But when you are drawing the diagram of yours, because in here we have to draw a diagram. Don't say that now my diagram will look like this. I will have a horizontal ruler like this. Then I will have a knife edge. I will have a wooden block which is sleeping there like this, lying horizontal, the way you see this one. I'm having another one which is vertical, and I'm having another one which is vertical like that. We just need one wooden block. You will say that I'll place my wooden block there. You get that? Then when I place my wooden block exactly at that point, then I put on a knife edge and balance with the ruler. You don't need to put a lot of diagrams. Now, the next part is balancing. I want someone to come and balance for me this one until the balance of the horizontal. You balance of the knife edge until the balance of the horizontal. Let's see how I put something. This one stand alone. can stand on this one. That is the value. Then from there, you tell us your value at which it is balancing. Or we change the knife blade, maybe the problem is the knife blade. You can change the edges, try to balance also that one. That one, I think that one is okay. You can read off the value. Yeah? The value is what?
It's 52.
52, eh? It means our center of gravity is equal to 52, eh? Now, when we are dealing with this experiment, there are some stuff that has to be held constant. Now, it means here we shall be playing along with the center of gravity. We shouldn't divert from the center of gravity. Now, here when we are choosing the variable, we shall set the fixed variable. This one we shouldn't tamper with. Because whenever you tamper with this one, the values will be changing. Then we shall make our center of gravity the fixed variable. We are not supposed to change it. Now it means whenever this ruler moves away from the 52 marker, you bring it back to the 52 marker. Then from there, we choose and say, among this side, this and the other one, which side should we make fixed? That whenever I change this, then I have to move this body the other side to bring back the balance. Then we usually make the one that has a fixed mass to be the what? To be the one on the independent variable. And here we are going to use a mass like this one of them which is of 100 grams. Now it means where I will have a mass of 100, like on my diagram, I fix a mass of 100 this side. Now I will say that the distance from where the mass is up to the center where I'm pivoting from, where the knife edge is. I say this is the distance D1. Now I will say this one will be my this one will be the independent variable. That whenever I change this, then automatically I will get a change in the masses where I want to get the relative density from. Now the masses I can tie them from a string, these masses, where I want to obtain the relative density, and I mark this one as D2. Meaning whenever I change D1, I expect D2 to change. You see that? Now this is where we come to data representation. We present data in the table for neatness. Now it means we shall draw our table neatly well. And we say that our table will contain distance D1 which I will be changing, but it will be in centimeters. Then I will also obtain other values of D2. Just like that. Then you close your table well. Then you choose also the values you want to use. That's why these values shouldn't be the same. For me, I may say I'm going to use 12.0 centimeters, then I go to 13.0 centimeters, then I go to 14.0 centimeters, I go to 15.0 centimeters, then I will end with 16.0. Why am I adding 0.0? It is measured, it is equal to what? Yes, a meter rule, its accuracy. It has an error of what we call plus minus. Whenever you are reading here values, it might be in the 31, then it goes to 32, then it can be in the middle of 31 and 32. Which value will you take? Now you choose it depending on your own will. And you say, I'm going to take a 31. Another one will say, I'm taking 32. Now that divergence of 0.5 is the error. That's why we put on point the error. the decimal place for the error. Due to the fact that you have landed into the middle, but you are deciding which part should I take. You get that? Should I go for point? Like I take 31, I take 32. You are in the middle, you don't know what to take. Now that is the error we're talking about. These are the zeros. Due to the apparatus we are using. Now we are going to balance horizontally, but we have to fix this one at 52, our COT, fixed variable. Then from there where we have a standard mass, we read off 12.0 centimeters. Then we adjust this one until our ruler balance is horizontal. But this one we have to adjust as it is in water, because we want to get relative density, and we know that when we get relative density, we have to also put into account that we have to multiply by the density of water. Now, there is no way you can fix this one onto the ruler. What we do, we use a thread. This is the use of this thread I was talking about. Then you come and use a thread, you tie your mass. This is the standard mass of 100. Some of you will say that you are talking about we are using the principle of moments, but where are moments coming in? Moments will come in because we know at balance, the clockwise moments they are equal to the what? Anti-clockwise moments. At balance, it means if our ruler balance is horizontal, the forces that will be taking the other side has to be the same force that we will take the opposite end. Now we tie our, like you don't need to tie this one onto the meter rule. You just tie them, you make a loop that you just put into the ruler, and for easy adjusting than someone who has fixed the thread permanently onto the ruler. Then our masses, which we want to get their relative density, I'm going to tie both of them onto the thread. And then I'll tie this onto the thread. Then I will again tie also this one onto Then when I tie them onto the thread, then I have to make a loop, which I will be inserting into our ruler so that it can balance. Now, someone is going also to come and balance. Because for me, I can balance this one the full set. Now, what you are going to do, the ruler should remain at 52. It shouldn't move away from 52. Another thing, we make this one a fixed variable. This ruler has, this part has to be, you count from 52 going this side 12 centimeters. From 52 going this side 12, then you'll be adjusting this one until the ruler balance is horizontal. This one is easy. Someone should come and balance. But when you are balancing, you make sure these masses are into this one. It means you can dip them at a first like this. Now, when I'm to adjust this mass, I'll move this, the tube close, then I also move this because I don't want them to move out of the what? You get that? It is the same saga if I'm to balance also this side. I feel like this side is heavier. I don't know why. This side is heavier. If you observe well, this side is heavier. I'm not balancing. Now it will try to balance. Someone should come and start balancing. You maintain our fixed point at 52 at the same. You make the other side to be at the 12 centimeters, then you adjust this side. Make sure the ruler is seated at 52 mark. It is too F, it means you have used a different. Okay, let's try. Okay, let's say change here our values. Since we are the one doing the experiment, use it whether and see whether it will balance. 20. Is the 20 balance here? It is still heavy the other end. Use it out. No, we have to count from the starting point, from the COD here, make it fixed. We hit balance, you show the other side. It will balance. Now let's first get some values. Now it will hit balance again. The other side is heavy. Now it will try. Now we take a value that is 1. Now what is the value from here up here? That you want to mark. The value is like what?
It's 27.
We begin with the 27, because we have seen that with 27 it will work, then 27.0, then I can go to 28.0, then I can go to 29.0.
Must I make it 30?
I go with 30. Okay, 30.0, then I'll go to 31.0, then I go to 32.0, then I go to 33.0. I can also add from there 4 values. But let me add 51 or 34.1. Then balance, give us the other value. The value is what?
28.2.
28 is impossible. You see that the gap is too small.
This side what?
You count from here up to when you reach there.
7.
$19.8. Then we go to the next value. Now we change to 31. This side, like that. 31. Now what value will balance? Don't forget when it touches the test tube, all that measuring cylinder, you extend the measuring cylinder, that one should be free in space. You shouldn't feel it touching the what? The walls. It shouldn't touch the walls. When the fluid is touching the walls, you extend it to the other end. Then what should I write? If you feel like this part is heavy, it means you have to move this side. This part is still heavy. That's why you see it bending, going around this area. You read. 79.2.
It's 19.2.
19? Are you sure? Why is this the first one is 19.8? But I'm subtracting both because I remember my COG is 52. And I'm seeing you are saying minus 52.
It's -52.
Minus 52. You get 19.1.
22.
It means the first value is wrong. What made it wrong? That is 19 point what?
22.
It means the other one was colliding with the walls of the city. Now it means we repeat the other first value so that we get the right one. You go back to 30. It is heavy this side. Move going outwards. Now what is the value?
It's 76. Minus 52. That is 24.
Yes?
94.
Impossible.
Teacher.
It is started from
When she has said 76. Then I said
70.6.
and you have said 76.
18.6. This one I can now read. 18.6, Then you record off the next value, then also physical is out. We don't want physical feel like we are segregating this. We are gender sensitive. So I think we are gender sensitive. 32, independently, 32. Move. You can move this side slowly to balance. 17. I started to 17.5. We shall stay until the end. Then it is to go there. 13. You feel at home. Then the last one, I think. The last one should be
Shakira.
Shakira, you come in. At 33. Don't forget to push the cylinder on the other side. But we can use that thing when we are using the benzene. For that we don't usually push the cylinder and other stuff. We can repeat the same using the benzene. Then Shakira go in for the last value. Because I've put the pen here. Increasing, then this one has decreased, I don't know why. Then it has followed the same trend. Go for the last value. But even if you get a wrong value within the middle, during the line of basic fit, you remove all those errors. 34. Your balance is at 34 this side. The independent is at 13. You shouldn't move out from 52 there. If you see it going down the other side, it means the other side is heavy. Then you move towards the pivot. Extend towards the pivot. Now, if you see it is heavy this side, then you move away from the pivot. But you go slow. But you can leave it there. Twenty. 20.1. Don't say just the 20. You say 20. Now, these are the values of our ones that we are going to plot. You got a graph of D1, you got a graph of what? Dependent here, independent here. You get that? We want to see how these independent values, these are the axes. We say x-axis, y-axis. Then x-axis contains the values that are controlling the whole experiment. It's the x-axis. Now, the values that we are controlling our whole experiment, they are the D1 values. Now we shall represent the independent D1 centimeters here. Because they are the ones that they are controlling our experiment. Now we want to see how these values do vary along with this one. How are they moving the points? How are they distributed along with the y-axis, which we call the D2 in what? Centimeters. You include the arrows. This one is so important in practicals. We see that even if we add the other points, or we add other points going down, it will be the same. Don't make it fixed without including this one. Then it should start from any value you want, but the reason why we make these values, we choose them for our own, so that we can get the clear pattern here down. When you overchoose the values stagnantly, then you will fail to get the pattern. Here you can know that, here you can put 29.0, then here 30.0. You get that, 30.0. Then I can go to 31.0. You get that, now I'm having a trade, now meaning each of these big boxes is 1. Meaning each small one is 0.1. You don't need now to calculate everything as calculated. So, you get that. Each small one is 0.1. The big one is 1. You get that. Then here you will change, you will choose the trend depending on the value you have. We get the highest value minus the lowest value, divided by here, divide by 100. Then you get the number for the big one. In the 10, no, when you divide it by 10, you get the number of the big ones. Each big one. But for us, we are more interested in those smaller ones in the graph paper. If you know the graph paper, those small lines which are there, we are interested in those ones. That's why we divide by 100. Then the value we get, we mitigate depending on, we know the physics from all levels. You know that our values have to end with either 1, they end with a 2, they end with a 2.1, 5, and they end with a what? 5. Now, when you divide here, a lot can happen. Now, we try to divide this one and show you. The highest value of ours is 20.0 minus the lowest value, which is 18.6, 17.5. 17.5 is the smallest value. Then divide by 100.
0.025.
It is direct 0.025. That one we are just lucky. 0.025. Now that is the value of each small one. When you are counting from the graph paper. That is a small one that passes, that is its value. Now it means if we want to plot these values, it will be too easy. Because if I want to plot this one, I get it 18.6 divided by the value of the smaller one. Then it will give me, try to divide 18.6 divided by 0.025.
It's
7.44. 744. Now it means for small ones, I'll count 740 for small ones. You get that? Now it means your scale, everything will depend on your scale. And now if you begin at 0, it means you need a lot of values here. Now we have to go on lowering the scale depending on this. Now, the procedures, the way you have been doing it, it's the way you write here the procedure. You say you have placed a knife edge onto the what? The wooden block. Then you say that a knife edge is placed, or a knife edge was. We use the two tenses here in the report. You say a knife edge is placed, or you can say a knife edge was placed. You get that? Then you are placed on a horizontal ruler to measure the COG. You say that the horizontal ruler is placed onto a knife what? A knife edge, and is balanced until a point is found when the ruler balances what? Horizontally. Then that point which is found when the ruler balances horizontally is read off as the what? The COG, and you give its value, that the value was equal to 0.01 centimeters. You include it in your procedures. You see that? Then from there, you say you have now placed the independent variable of yours at a distance of 30.0. Then you have adjusted these masses that are into the water. You get that? Then when you adjust the masses that are into the water, then you find a point at balance when the ruler balance is horizontal. Already this one, we know it because it is a fixed, but we are looking for this one. These are the values that we are recording. Then you don't need to talk for all that you have balanced with the 30, you have obtained 18.6. You have balanced with 31, you have obtained this one. You get it? You say that the experiment is repeated with the different values of D1 and the corresponding values of D2 are obtained. Or the experiment was repeated with different values of D1 and the corresponding values of D2 were obtained. Now that is Pululu, you say when obtained. Then from there, those are the procedures for you. Then you end the procedures. You don't include the table near the procedures. Then the next part we go for the errors. What are the problem you have encountered? One of you, I think we were remembering that we have changed this knife edge. At first it wasn't balancing. When we changed it, then it balanced. Then you talk of that one. The knife edge was not sharp enough to allow balancing, but you changed it. You don't say that you buy a new knife edge, you are not mitigating now. You are now just providing alternative, but you want in the limited resources. You get that? In the limited resources, we have seen we have changed them. Now we are making things formal. We are just making things formal. You say that now in the mitigation part, you have changed it until you have obtained a sharp edge. You get that? You see that the ruler was not balancing well. What were the problems apart from a knife edge? What do you think brought about the ruler? Now, again, it is not balancing well. What were the problems? Those are the two tables we are dealing with, they are not at the same level. The masses also had the problem that the masses were also leaning against the what? The walls of the measuring cylinder. Now, what mitigation can you make? Yes, you can get a large container or alternative without changing any apparatus. You want to use that apparatus.
We should be moving this.
Now, what you can say, yes, moving is okay, but we can say that we should work when the masses are in the central part of the what? Of the measuring cylinder. When we see that the masses are moved from the central part, then we extend the measuring cylinder a bit. You get that until we balance and it balances horizontally. Also, if you remember at first our table was shaking, until we pressed some thing down. You can state it also because we have made it when you are conducting the experiment. Then the table was shaking, but at the end I got some water top. But that is what we call the mitigating. But for you will say the table was shaking, we removed it, we brought a new one. You are not mitigating, we are just replacing. But we want to work in the limited resource. Everything of ours is within the limited resources. Now the next part will be data presentation is this one. And one of them is drawing a graph here. You draw a graph. I want you people should draw this graph. I will need to see it. how you have drawn this graph. Then from there, you will calculate the relative density. I think relative density will be the what? We know from here, we can tell, because here we are using principal moments. It will be this one when multiplied by this one. You get that? It has to be the same as when we multiply the weight here. We multiply it by here. Now it means what we are obtaining, these were the values when we are in what? In water. If you still recall, it means you have to conduct the experiment when everything is in air. To get weight in air. You get that?
Yes.
Now we are going to obtain the weight in water because we have to, like, this is the same experiment you used to conduct when you are determining the unknown mass. Given a 100 kilogram mass, a 100 gram, you have this distance, you have this and this. You put a graph of this against this, the slope will be giving you the combination of all these ones. If you still recall, the other one will be determining the unknown mass from all over. Now, what we shall do next is interpreting data interpretation. We interpret data after drawing a graph. Then from the graph, you choose for yourself the line of best fit. I want to see how you will do that. You know this is competency based. I just guide you how you can do it, then you can try. If you fail, then I can also come in and guide again. I want you to go to Ghana, schedule this thing. You write the report well. You know, because the procedures now they are used to your head, because you've been the one doing it. Now the procedures were there. I want this format to look as it is, well elaborated with what you go on, you indicate this one weight, you draw a neat diagram. I want you to experiment. One will be on to this. You review, like you still recall the values 600 and 600, but that one doesn't matter because we have the weights here. This one doesn't have a graph. We took one reading. This one we shall just write procedures. This is independent, we shall skip apparatus diagram procedures. We shall do this, we skip this, we write this and that. We go to errors and mitigation, data presentation and interpretation, we shall combine it together. You get that? Data presentation and we shall combine it together. Then we do one calculation. From calculation, we conclude. You get that? Then from there, this one, we shall do all, because everything has manifested. Then we shall need to see how everything will be there. The table for you, I've left it here, so that you can get the values and plot.
Yes.
Now the only part you will do, getting the weight in air, but weight in air, we know it is what? Weight in air is 2.0 newtons. First using the spring balance. Now the next part is yours, you people.